Okay, in this lecture we're going to finish our section 5.3 material on diagonalization of matrices. Now we saw in the first part of this section there was a result known as the Diagonalization Theorem, which said that a matrix A, a square matrix A, is diagonalizable. That is, it can be expressed in the form P, D, P inverse, where P is some invertible matrix and D is a diagonal matrix, if and only if that n by n matrix has n linearly independent eigenvectors. So we had looked at some examples where we can use a diagonalization of a matrix to compute large powers of that matrix. And we did one example where we found a diagonalization of a 2x2 matrix. So let's consider some more complex examples now, say diagonalization of a 3x3 matrix. So in the following example, we're asked to find the diagonalization of the matrix A, which is 3x3, if possible. And as a hint, we're given the eigenvalues of this matrix A are 2 and 8. So one of these has multiplicity 2. So let's take a look at the corresponding eigenvectors. So we need to show that there are 3 linearly independent eigenvectors for this matrix A in order for it to be diagonalizable. So starting with our first eigenvalue, let's say if lambda 1 is equal to 2, then to find an eigenvector, we're looking at the equation A minus lambda, which was 2, times I, times some vector, let me call it x1, or maybe I'll just call it x for simplicity, is equal to the 0 vector. And we're looking for non-trivial solutions x. So expressing this system as an augmented matrix, when we're looking at A minus 2 times I, we're subtracting 2 from the diagonal entries of A. So we have the matrix 2, 2, 2, 2, 2, 2, 2, 2, 2, which we are then augmenting with the 0 vector, since this is a homogeneous equation. And it's clear that our rows and columns are identical. They're linearly dependent. So there do exist non-trivial solutions of this equation. So it's easy to see that this matrix is row equivalent to the matrix 1, 1, 1, 0, 0, 0, 0, 0, and 0, 0, 0, 0. So we see that here x2 and x3, the second and third components of an eigenvector, are free variables. And from our first row of this augmented matrix, x1 is negative x2 minus x3. So in summary, an eigenvector x would have to have the form x2 times the vector negative 1, 1, 0, plus x3 times negative 1, 0, 1. So I can choose any values I want for x2 and x3. So choosing them both as 1, I would have, or choosing either one of them as 1 and the other as 0, I would have 2 eigenvectors as these 2 vectors shown here. Let's call these v1 and v2. And we can see from inspection that v1 and v2 are linearly independent since they are not scalar multiples of one another. So we can say here a basis for the eigenspace for the eigenvalue 2 is the set of these 2 vectors, v1 and v2. They are linearly independent and span the eigenspace, the set of all eigenvectors. So if we consider our other eigenvalue, lambda 2, which was equal to 8, then to find eigenvectors, we're looking at the matrix A minus lambda times I, so A minus 8I, times some vector x is equal to the 0 vector. So writing this as an augmented matrix, we have A, and then we're subtracting 8 from the diagonals. So we have -4, 2, 2, 2, -4, 2, and 2, 2, -4, which we are augmenting with the 0 vector. So here for simplicity, we won't show all the details of the row reduction, but this matrix is row equivalent to the matrix 1, 0, -1, 0, 0, 1, -1, 0, and 0, 0, 0, 0. So when we're looking at eigenvectors, or solutions of this equation, x, we see that x3 is a free variable, since our third column is a non-pivot column, and using the first two rows of the augmented matrix, x1 and x2 are both equal to x3. So any eigenvector has the form x3 times 1, 1, 1. So if I choose any value, any non-zero value for x3, I get an eigenvector. So let's call this vector v3, which would be a basis for the eigenspace corresponding to lambda equals 8. So here I'll say a basis for the eigenspace for our second eigenvalue, which was 8, is the set consisting just of v3. We've got a one-dimensional eigenspace there. Now again, it's clear that v3 is linearly independent from v1 and v2, since none of these are scalar multiples of one another. So here I might say clearly the set v1, v2, v3 is linearly independent or we can make use of theorem 5.2 that we had seen earlier in this chapter, where if we have distinct eigenvalues, their eigenvectors must be linearly independent. So here, the eigenvector for 8 is linearly independent from the eigenvectors for the eigenvalue 2. And even though the eigenvalue 2 had multiplicity 2, since our basis here consists of 2 vectors, we see that v1 and v2 are linearly independent because they are not scalar multiples. Therefore, the set of these 3 must be linearly independent. So A is diagonalizable, and to find the diagonalization, we let our matrix P be the matrix which has these eigenvectors as its columns. So -1, 1, 0, -1, 0, 1, and 1, 1, 1. Or again, because the x2 and x3 were free variables in these examples, or in this example, any non-zero scalar multiple of these column vectors would also work. And then D is the diagonal matrix whose entries are the eigenvalues. So here 2, 2, and 8 with zeros elsewhere. And again, if we check that, or we can check, let's see, we want A to equal P, D, P inverse, which is true if and only if AP is equal to PD. So you can verify that the product of A times P is equal to P times D Therefore, this is a valid diagonalization of that matrix A. And we could use this to find A to larger powers. So let's look at another one. In our next example, we have the exact same sort of problem. We're supposed to diagonalize the following matrix if possible. So it's, again, a 3 by 3. And as with the last example, we're given a hint. The eigenvalues of A are provided as 1 and -2. So let's see if we can find a set of 3 linearly independent eigenvectors. So this matrix is diagonalizable if and only if there exists such a set. So if lambda 1 is equal to 1, then to find corresponding eigenvectors, we're considering A minus lambda times I. So here A minus 1I times the vector x. We're setting that equal to the 0 vector. So expressing this system as an augmented matrix, we take A minus the identity, so subtracting 1 from the diagonals. We have 1, 4, 3, -4, -7, -3, and 3, 3, 0. And we're augmenting that with the 0 vector. So again, for simplicity, we won't show all of the details of the row reduction, but this matrix is row equivalent to the matrix 1, 0, -1, 0, 1, 1, 0, 0, 0, augmented with the 0 vector. So we see that x3 is a free variable, and using the first row of our augmented matrix, we see x1 is equal to x3, and x2 is the negative of x3. So any solution, which would be an eigenvector, has the form x3 times 1, -1, 1. So a basis for the eigenspace for lambda 1 would be this vector v1, since the set of eigenvalues would have to be a scalar multiple of that vector. So here we'll say a basis for the eigenspace for the eigenvalue, lambda 1 equals to 1, is the set consisting just of v1. So for our other eigenvalue, lambda 2 equals to -2, we're looking at the equation A minus lambdas, which was -2, so A plus 2i times a vector x is equal to the 0 vector. And we're looking for non-trivial solutions. So expressing this as an augmented matrix, we're adding 2 to our diagonal entries. So we have 4, 4, 3, -4, -4, -3, and 3, 3, 3, augmented with the 0 vector. So this matrix is row equivalent to the matrix 1, 1, 0, 0, 0, 1, 0, 0, 0, augmented with the 0 vector. So we see here that column 2 is a non-pivot column, so x2 would be a free variable, and any eigenvector x would be expressed in the form x2 times, well, we see from our first row of this matrix, x1 would be the negative of x2. x2 is exactly 1 times x2, and then the second row of this augmented matrix says x3 has to equal 0. So this eigenvector, let's call it v2, would form a basis for the eigenspace for the eigenvalue -2. So here, a basis for the eigenspace for lambda 2 equals to -2 is the single vector v2. So by inspection, we see that v1 and v2 are linearly independent since they're not scalar multiples of one another. However, every eigenvector of this matrix, we've just said, has to be a scalar multiple of one of those two vectors. So we only have two linearly independent vectors, eigenvectors for the matrix A, which is 3 by 3. So here we can say there are only two linearly independent eigenvectors of A, which is a 3 by 3 matrix. So by the diagonalization theorem, the matrix A is not diagonalizable. So there is no factorization of this matrix of the form P, D, P inverse. It's not possible for this matrix. So what we've seen in the last couple of examples provides sort of a little insight for the following theorem, which gives a sufficient condition for a matrix to be diagonalizable. So this is theorem 5.6, which says an n by n matrix with n distinct eigenvalues is diagonalizable. So in order for a square matrix of dimension n to be diagonalizable, it must have a sufficient condition would be that it has n distinct eigenvalues. So that is, if a matrix has n distinct eigenvalues, then it must be diagonalizable. So the proof of this is pretty straightforward. So let's suppose that a matrix does have n distinct eigenvalues, and let's suppose that the vectors v1 through vn are the eigenvectors corresponding to the n distinct eigenvalues of our matrix. Let's call it A. Now, we had seen in our first section of chapter 5, theorem 5.2 said if we have n distinct eigenvalues of a matrix, the eigenvectors corresponding to those values form a linearly independent set. So here by theorem 5.2, this set of vectors v1 through vn is linearly independent. So by the diagonalization theorem, that is theorem 5.5, if an n by n matrix has a set of n linearly independent eigenvectors, it is diagonalizable. So that's what we've just established. So A is diagonalizable. So a word of warning about this theorem. This is a sufficient condition. It is not a necessary condition. So it is not required that a square matrix n by n, for instance, must have n distinct eigenvalues in order to be diagonalizable. So as an example of that, if we look at our example that we started this lecture with, we had the matrix A, which was a 3 by 3 matrix here, and it only had two distinct eigenvalues, but it was diagonalizable. We didn't have to have three distinct values in order for it to be diagonalizable. But we are guaranteed if a 3 by 3 matrix does have three distinct eigenvalues, then it will be diagonalizable. So a sufficient condition, but not necessary. So making use of this theorem, let's consider the following problem. We're asked to determine if the following 3 by 3 matrix is diagonalizable. And we notice here that A is a 3 by 3 matrix which is upper triangular. All of the entries below that main diagonal are 0. So recall that the eigenvalues of a triangular matrix are just its diagonal entries. So let's start by saying since A is upper triangular, its eigenvalues are the diagonals. Lambda equals to 1, 4, and 6, which are all distinct values. None of these is the same. So here our matrix A is a 3 by 3 matrix with three distinct eigenvalues. So by our new theorem, theorem 5.6, this matrix A is diagonalizable. All right. So for the last part of this section, let's consider matrices whose eigenvalues may not be distinct. So if we have a square matrix, say an n by n matrix, which has n distinct eigenvalues with corresponding eigenvectors, v1 through vn, and we take P to be the matrix whose columns are those eigenvectors, then we know P is automatically invertible because its columns, which are eigenvectors corresponding to distinct eigenvalues, are linearly independent, as guaranteed by theorem 5.2. And the invertible matrix theorem says if we have a matrix, a square matrix, whose columns are linearly independent, then it must be invertible. However, if we have a matrix A which is diagonalizable, but it has fewer than n distinct eigenvalues, we saw it's possible that we can build a matrix P in such a way that P will be automatically invertible. Recall that we need P to be an invertible matrix in order for this factorization to work. So the following theorem, 5.7, gives us a technique for constructing such a matrix, and will tell us when our matrix A is diagonalizable. So here, let's suppose that we have a matrix A, which is a square matrix, n by n, which has distinct eigenvalues lambda 1 through lambda p. Where p is less than n. So it doesn't have as many distinct eigenvalues as its dimension. So for values of k that are between 1 and p, the dimension of the eigenspace for the eigenvalue lambda k is less than or equal to the multiplicity of the eigenvalue lambda k. So the eigenspace must have dimension at most equal to the multiplicity of the eigenvalue. Now part B of this theorem says the matrix A will be diagonalizable if and only if the sum of the dimensions of the eigenspaces is equal to n. And this happens if and only if two conditions hold. The characteristic polynomial must factor completely into linear factors. And 2, the dimension of the eigenspace for each eigenvalue lambda k is equal exactly to the multiplicity of lambda k. And then the third part of this theorem says if A is diagonalizable and B sub k is a basis for the eigenspace corresponding to that eigenvalue lambda k for each value k, then the total collection of vectors in the sets of bases B1 through BP forms an eigenvector basis for Rn. So let's consider one last example, which will make use of this theorem. So here we have a 4x4 matrix A, and we're asked to diagonalize this matrix if possible. So here we can save ourselves a little bit of work if we notice that this matrix is lower triangular. All of the entries above that main diagonal are zeros. So for a triangular matrix, the eigenvalues are exactly the diagonal entries. So here we can immediately say that the eigenvalues of the matrix A are lambda equals to 4 and 2. And notice that both of these have multiplicity 2. So we need to determine whether we have a set of 4 linearly independent eigenvectors for this matrix in order for it to be diagonalizable. So if we have our first eigenvalue, lambda 1 equals to 4, then to find eigenvectors, we're considering the equation A minus lambda times I, so in this case A minus 4I, times some vector x is equal to the 0 vector. So expressing this system as an augmented matrix, we have a 4x4 coefficient matrix where we're subtracting 4 from the diagonals of A. So our first row is 0, 0, 0, 0. Our second row becomes all zeros when we're subtracting 4 from the diagonal. And our third row becomes 0, 0, negative 2, 0. And our last row is 1, 0, 0, negative 2, which we are then augmenting with the 0 vector. So clearly, there are non-trivial solutions since we have free variables. And we can see pretty quickly that this matrix is row equivalent to 1, 0, 0, negative 2, 0, 0, 1, 0, and then our last two rows being all zeros, augmented with our 0 vector. So we have, for this matrix, 2 pivot columns and 2 non-pivot columns. So here, x2 and x4 are free variables. Using the second row of this augmented matrix, we see 1x3 is equal to 0. And using our first row, 1x1 is equal to 2x4. So our set of solutions would be vectors of the form x2 times 0, 1, 0, 0 plus x4 times 2, 0, 0, 1. So these two vectors, let's call them v1 and v2, are a basis for the eigenspace corresponding to lambda equals 4. They span the set of eigenvectors, and clearly they're linearly independent since they're not scalar multiples of one another. Now for our other eigenvalue, if lambda 2 is equal to 2, then to find eigenvectors, we're looking at the equation A minus lambda I, so A minus 2I times x is equal to the 0 vector. and we have the matrix where we're subtracting 2 from the diagonals of A. So we have 2, 0, 0, 0, 0, 2, 0, 0, 0, 0, 0, 0, and 1, 0, 0, 0, augmented with the 0 vector. And this is the system we're trying to find non-trivial solutions of. So we can see pretty quickly that this is row equivalent to the matrix 1, 0, 0, 0, 0, 1, 0, 0, and then 2 rows of all zeros, augmented with the 0 vector. So we see from our first 2 rows of this matrix that x1 and x2 are both 0, and then x3 and x4 are free variables. So any solution of this system, x, has the form x3 times 0, 0, 1, 0, plus x4 times 0, 0, 0, 1, where x3 and x4 are free. So these 2 vectors, let's call them v3 and v4, are clearly linearly independent from one another, since one is not a scalar multiple of the other. And then the vectors v1 and v2 are linearly independent from v3 and v4 because the eigenvalues have different values, or they're distinct. Now, another way that we can, so that means then the matrix A has 4 linearly independent eigenvectors, and so it's diagonalizable. Now, another way that we could show that this, or justify that A is diagonalizable, is by making use of theorem 5.7. So we had here 2 eigenvalues, which were distinct, 4 and 2, both of which had multiplicity 2, and the dimension of the corresponding eigenspace for each of those eigenvalues was 2. Our set of eigenvalues is spanned by 2 vectors in each case, which is the same as the multiplicity of those eigenvalues. So by theorem 5.7 part B, so let's say by theorem 5.7, A is diagonalizable. And to find our diagonalization, we're going to let P be the matrix whose columns are linearly independent eigenvectors. So V1 was 0, 1, 0, 0. V2 was 2, 0, 0, 1. V3 was 0, 0, 1, 0. And V4 was 0, 0, 0, 1. And then D is the diagonal matrix whose entries are our eigenvalues, which were 4, 4, since we had multiplicity 2, and 2, 2, since 2 was an eigenvalue of multiplicity 2. And all other entries are zeros.